Hello everyone, Jim Malis again. Let's keep talking. Let me try to do in the video, some of the videos that follow, I'm going to be doing problems. Again, that's a big part of what I try to do. But let me do, there's going to be videos where there's just more or less kind of a lecture, getting you used to some of the content that's going on. Sometimes that's contained within the context of solving problems. That's usually the way I like to do stuff. Other times it's just flat out, let's talk about the theory and then hook around and then talk about problems a little bit later. Or like I said, within the context of problems, we can talk about the theory. That's a good way to do it too. Propose a problem, then explain how it gets done, and a lot gets said. Okay. For right now, let me say and anybody can read this. I mean, this is for the 120 people. At least a good portion of it can be used for the 120 people. But it's predominantly going to be for the 209 people. The 120 people is mechanics, but non-calculus treatment. 209 is going to be with calculus treatment. So there might be some elements of this that the 120 people will not need to know, but there's a lot that gets said here that applies to everybody who's going to look at physics. So looking at the 209 book, the Katz book, first edition, chapters 10 and 11, chapters 10 and 11 go along the lines of talk about things along the lines of momentum, collisions, and conservation of momentum. So let's talk about that. What's momentum? I guess there's a short answer for that, I guess you could say, and then we can kind of take it from there. We can say that momentum's a vector, just like acceleration's a vector, just like force is a vector, just like displacement's a vector, just like velocity's a vector. So again, always when push comes to shove, make sure you're aware that it's a vector. Well, there's a lot to be said. The momentum vector, lowercase p, momentum vector is mv vector. Momentum's an interesting thing. Momentum is a vector, and in any closed system, when there's something going on and there's no external force acting on the system, bam, you put the system in motion and there's collisions going on, any kind of collisions going on. These things can bounce off each other perfectly, not losing kinetic energy, or they can go to the other extreme of, from bouncing off each other, not losing energy. They can go to the other extreme and stick together completely. Doesn't matter. Momentum is always conserved, period. If it's a closed system and there's no external forces, you're not bringing in any new mass into the system or taking mass away from the system, and there's no external force being applied, momentum is always conserved. That is a fundamental law of nature. Energy is always conserved. Momentum is always conserved. We will talk more. There's a few things that always happen to the best of everyone's knowledge that does physics. Some of the most brilliant people in the world. They will tell you that energy is conserved and momentum is conserved. So rotational. Later on, we're going to get into rotational momentum, angular momentum in a sense. When something's going in an angular type of path. Angular momentum is always conserved, linear momentum is always conserved, and that's what I'm dealing with right now, and energy is always conserved. We'll get more into this. I don't want to get too far off on this, but basically we said that energy in a closed system is conserved. Momentum in a closed system is conserved, no matter how many particles there are and no matter what kind of collisions take place. Whether they bounce off each other perfectly, that's called a perfectly elastic collision. That means the kinetic energy of the system doesn't change. Or if they stick together in which kinetic energy is not conserved, but somehow the energy is to be found somewhere else. The kinetic energy that was lost will go into heat energy or something else. So energy is always going to be conserved, but kinetic energy is not always conserved in a perfectly inelastic collision when they stick together. But momentum will always be conserved even in those circumstances, believe it or not. There's a lot that happens. You say, well, what if there's friction involved somewhere? Even there, the molecules, the atoms of the substance will gain momentum with the friction that is being generated. Momentum, one way or another, is going to always be conserved, period. Whether they stick together in a perfectly inelastic collision or whether they bounce off each other in a perfectly elastic collision or anything in between. Only in a perfectly elastic collision will kinetic energy be conserved. But the energy, even if kinetic energy is not conserved, that kinetic energy that was lost will go somewhere else and energy will always be conserved. So you got this. Later on, they got this thing called angular momentum. We're not going to go there right now, but we will go there soon, eventually. And there, angular momentum is always conserved. So I'm going to come back to that. There are a lot of connections in the rotational realm and in the linear realm. We saw that earlier, or we saw that in other places, depending on the order you're looking at my videos, I guess. But yeah, if you look at it in the order in which I'm proceeding with some of this stuff, we have seen that the linear realm and the rotational realm have a connection. They look alike. Remember how we said that, oh yeah, I could talk about VF equals VI plus AT. Yeah, I know. I could kind of extend that to that's the linear realm. In the rotational realm, I can go omega F equals omega I plus alpha T, etc., so on and so forth. And we looked at those kinematic equations. We're coming back to that eventually. Not now, but I want you to remember that. This is going to be useful when we're talking about these kind of phenomena. There's a lot of analogies that you're going to see, and it's going to help you visualize many things. It's a very important thing. It's a very important thing. All right, so we know all that. Let's kind of get back to the beginning. Momentum is mv. It's a vector. A lot of times I take the vector thing out of there. But you've seen that. Sometimes we just do that and we say, okay, let's write it like this. We got a magnitude. But let's be aware, push comes to shove, this is definitely a vector. But mv is what momentum is. Okay. So there's collisions that happen. There's a lot of things that happen. Let me try to kind of say a bunch of stuff, I guess you could say, that can kind of get us there to where we want to go. Here's the crazy thing. I always give this analogy here. If I'm standing on some ice where I really can't move, I'm wearing the wrong shoes. It's really thick ice though. It's a meter. The ice is really thick, and it is incredibly slippery. There's no friction, in fact. My mass might be 100 to 110 to 120 kilograms, whatever my mass may be. Because they have a mass of 100 kilograms. And there's a child that's got a mass of 20 kilograms. 5 times less the child is 1/5 the mass that I am in terms of their mass. And I'm standing there, they're standing there, neither one of us can move, and we got to get to the side of the lake that's frozen 1 meter thick. The child pushes me, and the child flies off when he pushes me, but I also fly off. The child's going to fly off. The child that's got 1/5 the mass that I have is going to fly off with a velocity, a magnitude velocity, that's 5 times the velocity that I'm going to have. Why is that? Well, initially, there's a lot of ways I guess we can say all this stuff. Initially, we know that neither one of, let me write it like this. I didn't put the vector thing on there, but it's a vector. Initially, I ain't moving, and the child ain't moving. Myself and the child, we are one system. We're not moving. We really, push came to shove, we can't move really because the ice is not letting us move. I mean, there's no friction. I can't move. We're standing here and go, okay, man, I got an idea. You push me real hard, I'll end up going that way, you end up going this way, and maybe we'll just, and if push comes, if you're carrying any kind of weights with you, throw the weights. When I throw the weight, I'm pushing against the weight. I'm pushing the weight away from me or throwing the weight away from me, but in a sense, I'm throwing myself off of the weight. So that's why a lot of times when you throw something and it's slippery, you fall. Because you threw the weight, but the weight kind of threw you. You pushed off of the weight, and got the weight to leave you, but you also pushed off of the weight and got you to leave the weight. That's why pitchers in baseball got problems with their shoulders sometimes. Because they're throwing the ball, but in a sense, they're throwing themselves off of the ball. They're pushing themselves away from the ball, they're leaving it, and the ball's leaving them. Initially, there is no momentum. Why? Because the kid and I are both standing still. The kid pushes me and ends up going, the kid is 1/5 the mass that I am, and he ends up leaving, I end up getting pushed, and my mass is M, and I end up leaving at a speed V that way. I end up leaving at a speed, or whatever. I end up leaving at a speed V going to the right, and the child ends up leaving at a speed going to the left. 5 times more than me. This is MV. 1/5 M times 5V is MV. It's a negative. Yeah, it's still going to be 0. The kid has negative momentum equal to my positive momentum in terms of magnitude. The magnitude of the kid's momentum. Why? Hey, the kid's not that massive. Yeah, he's not that massive. That's why he's going so fast. M times V for me is the magnitude of my momentum, and M times V for me is the magnitude of my momentum, and 1/5 M times 5V is going to be the magnitude of the kid's momentum, which is also MV. Make a long story short, the kid pushes me. The kid pushes himself off of me, but also pushes me. The kid goes flying because he doesn't have a lot of weight, doesn't have a lot of mass. He's got 1/5 the mass that I have, which means that he's going to move 5 times faster than I do. Yeah, no, I'm going to go 5 times slower than him, but I got 5 times the mass. In terms of magnitude of momentum, we both got the same momentum, and it's 0. How did we start? We started by not even moving. Yeah, and when we do move, we're moving in opposite directions with equal magnitude momentum, and if you do a vector sum, the momentums add up to 0. So they talk about something, let's say you start like that. Now, it could have been that the kid and I were both moving. The kid and I were both on a sled, and the kid pushed me off the sled, and he pushed himself off the sled, and before you know it, the kid's going faster forward. He's going faster than the sled, and I'm going slower than the sled because I got pushed off. If you add all those vectors together, it's the same as when the kid and I were both on the sled moving. Maybe we were going at a momentum of 100 kilograms meters per second. What are the units? Well, these are kilograms. These are meters per second. 100. If M is kilograms and V is meters per second, it's kilograms meters per second. Okay? So this is, like I said, so if I'm on some kind of a sled and the sled is going with a momentum, I don't know, the sled is going with 500 kilograms meters per second. 500 kilograms meters per second is the momentum of the sled. And the kid says, I don't know what the kid's thinking. The kid pushes me off. The kid goes flying off the sled onto the ice. He's not hurt or anything. And he just goes, and man, he's flying. He's going faster than the sled was going before. I'm going slower than the sled was going before because I got pushed off onto the ice, but I'm going the other way. If you add our momentum, the sled, me, and the child, as we're all off the sled, you add our momentum together, it's going to be the same as when we were all together. Momentum is going to be conserved. In the strictest sense, we are talking about vectors. You know that. You've seen that. Okay, so that's some stuff to kind of look at there for momentum. Well, okay, great, whatever. How about some other stuff? I mean, there's a lot here, so I'll try to combine the 2 chapters when I'm talking about this, and we'll see how we can kind of figure out some stuff that we can say about it. So if this is the case, you guys, what else do you want to say? What else can we say, I guess you could say? There's a whole lot we can say. We just got to be a little on the careful side, I guess, when we do some of this stuff. There's different ways you can look at this. I mean, for those of you without the calc background that are not in the calc-based physics, look at as much as you can without the non-calc background they'll try to give on some of this stuff. For the calc-based background, for 209, you're required to have a calculus base to it, so you got to know that. And you know that anyway. So let's see what we can say. Let's see what we can say. As we look at this, we, I guess, could say a lot of stuff. I mean, try to give a couple looks at it, I guess you could say. You guys remember force equals mass times acceleration? Okay, yeah, we got a gut feeling for that. We know if something's very massive, look, there's nothing very, if something's as massive as an aircraft carrier, and somehow something, some natural phenomenon, bam, fires it, accelerates it in such a way that is way beyond even the propulsion associated with its engines. If something the mass of an aircraft carrier gets accelerated greatly, there is only a great force that can do this. There's no such thing as, oh yeah, I'll tie this, I'll do my best to give this thing a pull. I could pull something as massive as an aircraft carrier if it was on a frictionless surface and I was somewhere where I had good traction. I could pull anybody. A small child could pull an aircraft carrier. Sure could. If the aircraft carrier was on a frictionless surface. Yeah, the small child's not going to pull it with a great acceleration. It's not going to give it a big jolt. Neither am I. Neither is anybody. Neither are 20 of us. But some great massive force generated somehow could give it a great acceleration on a frictionless surface. Just because something's in a frictionless environment, or even in space, doesn't mean you're going to give it, anybody can move it. Yes, but not everybody can give it a great acceleration. Force equals mass times acceleration. If something's massive and you're going to give it a great acceleration, there is only a great force that can give you that. If something is not massive and there's not a great acceleration, the multiplication there yields a small answer. It's as simple as that. Okay, so we got this. We've seen, okay, I've already delivered this argument. We've already, in one place or another, somewhere you're going to see that I've delivered this argument. The best way to deliver these arguments, guys, is in person. You're going to hear me say that quite a bit. The best way is people are person to person talking about things like that. They can interact a lot better. Okay, force equals mass times acceleration. I do have a bit of a question to ask. If you took, let me go non-calc for a second, and let's see what we can say. I'm going to make the argument, I'm going non-calc, guys. And I'm not putting a vector notation on here, but they are vectors. F is a vector, P is a vector, momentum's a vector. I'm going to make that claim. It is a true claim. The only way you are going to change the momentum of an object, and they're both vector quantities, F vector and P vector, they're both vectors. But the only way you can change the momentum of something, and remember now, I don't necessarily have to change its speed. If I change its direction, then I've changed the vector, I've done something with the vectors. The vector location of velocity I have changed. I do that with a circle. I do that with centripetal force. With centripetal force, I am constantly not allowing that object to leave the circle at a tangent. I am forcing it to stay in a circle. I am constantly forcing it to stay in a circle. I'm constantly putting a force on it to have it stay in a circle. I am constantly accelerating it. So what are you talking about? The magnitude of the velocity is the same. It's whipping around at 20 meters per second around that circle. Yes, it is. But I'm not allowing it to go straight. I'm constantly changing its direction. That's also an acceleration. Okay. You say enough things, you put enough trees in front of somebody, you're not going to see the forest. Or the other way, if you put enough forest in front of them, they're not going to see the trees. I don't know how the whole thing works, but you can confuse people a lot of ways. So let me tell you the reality. That's true what I just said. Now let's kind of just go and get a gut feeling at this basic level. What's happening here? If you change momentum over a unit of time, change in momentum divided by change in time, that will be a force. You have to put a force to have that happen. That is equal to, let's talk. I mean, let's just talk a little bit. So, dmv dt, well, mv is p. mv is p. And you end up getting this. For a particular v, and you end up getting this, and this kind of, that really kind of strikes you. Because that looks a lot like this. Isn't acceleration the change in velocity over the change in time? Yeah, it is. I'm sorry, forgive me. Yeah, acceleration is the change in velocity over the change in time. Force is equal to m dv dt. I'm going to get a little more rigorous about it. I'm going to say that force is all of this. Something you didn't, I never told you about this. I already told you about that. That right there is ma. In fact, forgive me, the D and the delta, there is a connection there. They're closer to each other than we might think. Force equals delta m delta t times v, momentarily constant, plus m delta v delta t. That is important. That's ma. That's the ma. Ignore this, and you got force equals mass times acceleration. Why on earth would I do this? Because I could be on a wagon, and I could be going underneath some canyon, and I'm driving a truck, and there's a wagon behind me, and rocks keep falling onto that wagon, so they're slowing down my truck. They keep falling on the tractor bed at this rate, and so that's kind of doing something to the circumstances. I might be driving a car and a truck, and there's somebody in the back. Hey, we're doing this physics experiment, and they're pulling all these rocks that are in back of the tractor bed. They're picking them up and they're throwing them off. They're throwing them off the tractor bed. Or we're driving by, and people are throwing watermelons at us, and we're catching them and putting them on the tractor bed. There's a lot of things that can happen. Or a rocket. What does a rocket do? A rocket loses mass. When it loses mass, it's going to have an easier time accelerating. So mass can be added to a system or taken away from a system, in a sense, within the system. I guess you could say, within the system, the mass can be located somewhere else, and it gets onto the truck. Or the mass is in the rocket, and it's being expelled from the rocket's engines. So this sort of accounts for that. So this is, Newton knew that this was certainly true in a vast array of circumstances. A special case, one could add. In the most general sense, Newton knew this. And in fact, Newton was one of the great foundational figures in the study of calculus. And you could say a lot of stuff. Again, let me say something and then not, that kind of lose the vector notation. I am making the claim that if you take the time derivative, you get the rate of change of momentum, you're going to get the force. The rate of change of mv vector, and this could be for a whole bunch of particles. Don't want to get into all the what ifs here, guys. Don't want to get into all the what ifs. I want to give you at least kind of a broad discussion of it. I think that's why we get into when you do problems, you get into a lot of what ifs. And there's some problems that really summarize everything very beautifully. Or other times, you got to do a whole bunch of different problems to kind of see the whole picture, or get close to seeing the whole picture. Let's go. the time derivative of this product, the derivative of a product, is the derivative of the first function times the second function plus the first function times the derivative of the second function. I kind of said it here in a little more generic way. For the people in the Physics 120 non-calculus based treatment of mechanics, this works. For the 209 people, this works. A lot of people taking classes that are calculus based or non-calculus based still have a calculus background. So I'm giving you some of the stuff to look at. If you lose the vector notation, as long as you're okay with that, I don't like to, I guess, what do they say? Never say never, never say always, right? But here you go. This is how force works. I know this is what we're used to seeing. M dv dt. M dv dt is ma. End of the story. There ain't no mass being lost. What if there is, though? In rockets, they are lost. This whole thing is what we're looking at. Whole thing is what we're looking at regarding that. Okay. This gets rather interesting. This is going to get us to the rocket problem. And there's manifestations of this as well. Let me see what I've already covered this in other places. I wasn't thrilled by the sound quality that I had in a video way beyond this time frame. Would have been months ago, but it is what it is. It's there for you. It is written out. I do have it in the notes, so you should be okay if I can't get to it the way I want to get to it. But let me say a couple things here. And I do have a lot of stuff in the notes. Like what I'm about to show right here, I have in the notes in Canvas, and anywhere else, I guess I'll be able to put those notes. If Canvas, whatever, however long I'm teaching or whatever, I'll try to have these in different places for you. But right now, it's just in Canvas, and that's all. That's the only place I need to have it because Canvas is active right now for us. We got this, and there's other. We have other stuff too. That's going to be pretty interesting for us. All right. Well, let's leave that and let's talk a little bit about a few things, and we can say what we can say regarding that. So we try to think here exactly what I want to, the path I want to take on this. There are numerous things here, guys. I think that the lion's share of this, always be reading the book. It is just about impossible to go through the book every chapter cover to cover on it. Every chapter would probably take way more time than you're going to have to look at it, and likely way more time than I'm ever going to have to try to go through it as well. I can always give you the highlights, and I always do give you the highlights. I try to give you the very strongest basis vis-a-vis the problems and vis-a-vis any discussions. The best we can do on that, I think we're pretty good. You also have the book, though. You got to be looking at the book. Make it make sense to you, and then look at what I'm doing and say, okay, here's what he highlighted, me, the teacher, or any other teacher for that matter, what they've highlighted, and then make the two kind of sync up a little bit when we do it. The best way to look at the stuff that's in the book is to read the book, and I know everybody's going to be doing that for me. They talk about the first and second rocket equations, and they say a bunch of things. Like I said, I'm trying to kind of, I just debate with myself how far to go with it. The book's got the great coverage, and I'll let them kind of handle it vis-a-vis some of that stuff. I don't want to lose the big picture by getting mired in too many of the specifics. I'm trying to give you a bigger picture. That's always the way I'm trying to approach this. For better or worse. Hopefully that's for the better for you guys. I'm really hoping for that. Well, they talk about rockets. They talk about the first rocket equation. They talk about the second rocket equation. Yet it's not easy to find somewhere. Let's just take a look at the first and second rocket equation. Will be contained in something I'm about to show you here, guys. Let me try to talk about it my way, I guess, which does not necessarily mean it's the best way, but it's going to be a way I think works pretty good for you guys. Okay, this and that and this are essentially the same statement. One's calc-based, one's non-calc-based. And this is really a big part of what they talk about when they talk about momentum, collisions, conservation of momentum, this is there. There is an interaction, a very close relationship, so to speak, between force and momentum. What is it? If you're changing momentum over any period of time, there had to be an external force that you apply. There had to be some force. This thing about external or internal, this is another issue in its own right. But if we're talking about, there has to be a force if there's going to be, if I'm going to take a snapshot, even of a closed system, if I want to look at one piece of a system. Perfect example, guys. If I went somewhere, there's a physics experiment, there's nobody around, it's very safe, there is a target 100 meters away or wherever it is. And I am going to stand horizontal with the rifle. And, it's a rifle and I'm firing at the target. I am standing, the rifle's standing still, the bullet inside the chamber is standing still, everything is standing still, so to speak. Bam! I fire the gun. The gun and me go backwards. The gun, I'm holding on to the gun and the gun throws me backwards. The gun itself gets thrown backwards and me holding on to the gun and I both get thrown backwards and the bullet gets thrown forward. The bullet acquires momentum moving toward your left. The rifle and myself, we acquire momentum going toward your right. The vector sum of the two is the same situation as the child having pushed me when we were both on ice. Momentum that way, they add up to the initial momentum. The initial momentum was 0. What are you talking about, man? That bullet's really moving. Yeah, so am I. I just ain't moving as fast because the gun and I are so much more massive than the bullet. The bullet's going at a great velocity. The gun attached to me, because I'm holding it really tight, the gun attached to me and the gun and I end up flying that way, but we're not going that fast because we're so massive. The bullet's not massive, but it's going really fast. And the two momenta are equal in magnitude, but opposite in direction, and they add up to 0. It's a big thing. So if that's the case, that's the way we're moving, guys. That's the way this whole thing proceeds. So that's a big thing. I was just trying, for some reason here, I'm just forgetting one aspect of what I'm trying to say here with this. Something else I wanted to say regarding that. So that's the big, so there's got to be, we talk about changing momentum and all this other stuff, even within the fact, that's kind of what I was trying, even within the fact that myself, the rifle, and the bullet were in a closed system, while the bullet is streaking toward the target, the bullseye, in this faraway field, nobody else around us and stuff, while it's going there's nobody around us and we're just doing this physics experiment, the bullet has tremendous momentum compared to what it used to have. Nobody's denying that. Yeah, but the person and the rifle attached to one another also have the same tremendous momentum going in the opposite direction. The vector sum of the two is 0. That doesn't mean that it's a good idea for me to go stand in front of that target when somebody's doing this physics experiment. Oh, hey, momentum 0. Yeah, the total momentum is 0. The bullet by itself has tremendous momentum. It's a similar argument. Okay, this is what I was just remembering, guys. It's a similar argument to saying that it's a similar argument to saying that, okay, there's, it's one of those cartoon things. Okay, faraway field, there's an explosive device, and there it is. It's got mass M. It's got mass M, and it's got no velocity, though. It ain't moving. From remote control, far away from everybody, so there's no momentum here. The initial momentum here is 0 vector. After the thing explodes there are masses everywhere. some this way, some that way, some this way, some that way, some this way. Well, you get the picture. If you add all of the momenta, the vector sum of all the momenta of the explosion, the sum of all the pieces of shrapnel, the sum of all the pieces of shrapnel, the sum of all the momenta of all the pieces of shrapnel in a vector sense, the vector sum of all those pieces is 0, just like it was right here. Again, what the heck does that mean? That means that the net momentum of the system initially, when the bomb wasn't moving, it wasn't moving at all. The net momentum of this mass M is p sub I vector equals 0 vector when nobody's moving. After it is exploded in this experiment far away from everyone, and there's pieces coming out this way in 3 dimensions. They're coming out. They're coming out that way. They're going in that way to the other. They're going in that direction that way. They're going in that direction that way. They're all over the place. The vector sum of all of those is 0 vector. Obviously, what I always tell my students is, yeah, don't ever, that means I can stand in front of that, this could be a hydrogen bomb. This could be an atom bomb. This could be a hydrogen bomb that they exploded in the 1950s when they were, blowing up atolls that were in the Pacific Ocean or something like that, atolls. Yeah, great. The vector sum of all the momenta, and they end up affecting the surfaces and other things end up flying all over the place. All of that stuff is 0. Yeah, that doesn't mean you need to go near that device when it's going to go off. Because this piece, though they may add up to 0, these guys do have a non-zero sum just like they do. You might add them up and get 0, but I don't want to be in front of that thing. The bullet's got a real momentum. So does the gun and I going in the other direction. Yeah, we add up to 0. It doesn't mean the bullet by itself is 0. Doesn't mean right here it's, so this is what's, I'm telling the obvious. I mean, if something explodes like that, accidentally or purposely, in a war or an experiment or anything like that, there's obviously danger because each piece does have a non-zero momentum, making it dangerous. The bullet did, the shrapnel does here. Okay. There's a lot of stuff they say, guys, and I'm going to try to make it, I'm going to try to go with the book, and then so when you read the book, the book doesn't bother you as much. Or when you read the book, I don't bother you as much. Hopefully I'm giving you some insight on the stuff. Okay. Well, let's stick with what we did right here. And let's talk. Let's just talk a bit. And there's a lot here. There's a lot of looks we can give this thing. I've already given some of those looks in other places, and I'll try to make that available to everybody as best I can. Again, the sound quality in some instances has been less than ideal. Notice when I say that, I'm just making sure my mic is on. Okay. So, but other times it just wasn't. In times past, things could have been a little bit better, maybe, but they could have been a heck of a lot worse too. So, all right. All right, we're saying a bunch of stuff. Let's talk about let me think here. Let's go with this guy. And let's talk about a rocket. And let's talk about some stuff that they say here. They make a claim. There's a lot of ways to write this stuff. So let me kind of agree with the book as much as I can agree with the book. And let's prove why the book says what it says. And let me agree with the book as much as I can. And then let me also try to maybe kind of go a little bit of my own way on this when we do some of this stuff. All right, they talk about the rocket equation and what the heck that means. I'm kind of telling you, stay right here and let's talk. The force, the whole thing here, what's happening here? And that's coming out from here. You got dp vector dt, so that's what force is, and that's dp dt. Let's talk. The rocket problem is basically this, guys. A rocket's a rocket. We are familiar in at least the generic sense of what rockets do. Rockets are not projectiles. Yes and no, I guess. We can, again, how many trees do you want to put in the forest? How much of a forest do you want me to put in front of you? Basically, here's what I mean. When I hit a golf ball, all the energy that I'm giving the golf ball depends upon how long the golf ball is in contact with the front of the club. As long as that ball is in contact with the front of the club, I am giving that ball, I am changing that ball's momentum, I am giving that ball an acceleration, I am making that ball into a projectile. Once it leaves the club, there is no rocket attached to the ball. There's not a rocket, it just goes. It's a when I throw a baseball, that's it. Once it leaves my arm, the energy that I'm imparting to it is done. We're assuming no air resistance, none of that. Okay, and it's going to go the way it's going to go. Gravity's going to work on it. Those are projectile type problems. You fire the old-fashioned cannonball from the 1700s. Once that cannonball leaves, it's not a rocket that's being fired. You know, it's not a surface-to-air missile or something or whatever. I mean, it's something different. The cannonball doesn't have a rocket on it, whereas the rocket does have a rocket on it. The rocket blasts off and it keeps expelling mass. While it expels mass, it is doing what? It's speeding up. Why does it speed up? The same reason when myself and the child were standing on a small lake that was frozen 1 meter thick, and there was no friction, and we're just standing, hey, we can't get out of here. You know, what's going on? Okay, you push me and I'll fly that way, you fly that way, and maybe we get over to the side. There's no friction, so let's just get there at least. Right now there's no momentum for either one of us. Zero momentum, the vector. And it'll be zero momentum if you add the two vector quantities. The child has positive momentum, or I have positive momentum going to your right, and the child's got negative momentum. They add up together on the straight line to zero. But we both get to the side though at least. The child pushes me, and then I end up flying that way. And the child ends up flying that way. The child lost for himself some of the mass of the system by throwing me off. I lost some of the mass of the system by the child throwing me off, and then I end up going that way. As the mass is being expelled from the rocket, ladies and gentlemen, the exhaust, as they say, the exhaust itself is being thrown like somebody's inside the rocket engine throwing baseballs. The more if I'm standing on something that's a sled and there's no friction, if I got all these baseballs in a real huge bucket and I pick them up and I start throwing them, I'm pushing off of the baseball, projecting myself that way. The baseball is getting projected that way, but my arm is pushing against the baseball to push me on the sled the other way. If I continuously do that, it's like I'm mimicking a rocket. The rocket is throwing exhaust in one direction, which means that the rest of the rocket that stays the rocket's pushing itself against the exhaust to end up going the other direction. This is Newton's third law. Actually, a lot of it is, to a big extent. I am pushing against that. A force was imparted, but I'm also imparting a force to myself, the same force in magnitude, but in opposite direction to go the other way. Okay. So I guess the rocket engine has a huge supply of baseballs, and there's some troll in there throwing the baseballs, right? And as the baseballs get thrown, the troll is pushing himself and the rocket the other direction off of the baseball. The baseball's getting thrown that way, and Newton's third law, you're going the other way. If you add in a vector sum, the rocket started with zero momentum. It has zero momentum, even when the rocket goes really fast. Just like when the bullet was going really fast. The sum of me and the rifle, my momentum, vector sum, with the vector sum of the bullet. When you add them together, it's going to be 0. Okay. So, some of what they're saying here. There's a lot can be said. They talk about the first rocket equation and the second. Now, they write it in a particular way, and I'll do my thing too, and we'll figure out what we want to say regarding this, you guys. So, delta VR vector, that's the rocket. The change in the rocket's velocity, the rocket that's the part of the rocket that's still intact without the stuff flying out the back end of it, the part of the rocket intact is the velocity of the exhaust relative to the rocket, that vector, times, again, it's a little, I don't know, I'm less than thrilled, but I think I'm less than thrilled in the way I would do it my way too. I mean, it's always inherently confusing. You got to watch out for the negative symbols, guys. One of the big problems you're going to see in physics let me stop for 1 second. Excuse me. One of the big problems you're going to see in physics, guys, is what's negative, what's positive. Kind of arbitrary. I kind of told you about that when we were dealing with potential energy, how that all played out. You got to have a good bookkeeping method. This is of interest. I don't see a negative symbol here, guys. I do not see a negative symbol here. Shouldn't there be a negative symbol? Well, yeah. I mean, if the rocket's going that way in the positive direction, and the exhaust is going that way, if to your right is positive, and to your left is negative, that's arbitrary in its own right. Call one of them positive, call one of them negative. That makes sense. Why are the signs the same? They're not really the same. Yeah, this guy gains velocity to the right. Positive. This thing is negative. A negative value. What's a negative times a negative? And how do I know it's negative? This is the mass of the rocket at some point after an amount of exhaust has been expelled. Delta M exhaust has been expelled. It's a small number compared to the initial mass of the rocket. A small number divided by a big number is a fraction less than 1. The natural logarithm of a fraction that is less than 1, the natural logarithm of a fraction that's less than 1 is a negative number. What is negative times negative? Positive answer. So that's how it works out. There's a lot of ways you can do this. You got to be careful. You got to be careful. Let me write a couple things down and let me kind of like rewrite it maybe the way I want to look at it a little bit. And we'll see what we can say here. That's the first rocket equation. They call this other one the second rocket equation. The force thrust VE R delta MR dt. What is going on here? Well, okay. This says if what is getting expelled from the rocket is the velocity of each particle that's getting expelled from the back end of the rocket, if that speed is great, that'll contribute to a lot of force to push the bulk part of the rocket that's moving the other direction. I want to find out how fast the rocket's going or how much force is being generated onto him. It's also the force being generated on the other particles too. They're going equal and opposite because initially nobody's moving. The change in momentum is 0. Change in momentum is 0. Are you telling me the change in momentum when I fire that bullet, that target, I'm holding tight to the gun, myself and the rifle fly that way, the bullet flies the other way. If you add our two momentums together, it's 0. Yeah, the sum of the momentums are 0. What's the net force on the system? I guess you can, on the whole system, our center of mass doesn't move. That's kind of weird in that sense. If you look at the center of mass of the system, when we're right here, the center of mass is going right down the center of my body, down this way. When the bullet gets fired, my center of mass moves a little bit. The center of mass isn't moving. That doesn't mean the gun and I are not moving. It doesn't mean the bullet ain't moving. Same thing with the explosion that took place. The center of mass doesn't change. The force external on the system, external force on the system is 0. The center of mass doesn't change. The center of mass of that bomb that exploded stays at the center of mass of the bomb. Yeah, that doesn't mean pieces aren't everywhere 1,000 meters away in every direction. If you do like a weighted average of where they are, the center of mass is right in the center. And that's somewhere the book goes into in a lot more detail than I'm going right now, but I just want to tell you that. So this right here, V vector VE at the rocket speed is dmr dt. So essentially at the end of the day, you guys, in non-vector notation, and I'm not saying it's a good idea, I'm not saying it's a bad idea either. Let's just work with the actual numbers we got here. As long as we know that everybody's kind of opposed to everyone else in terms of their motion. They're going in different directions. As long as we got that, you can, maybe it's a little easier on your psyche, I guess, when you got it looking like this. Mass of the rocket finally, which means it's a smaller number than mass of the rocket initial. You're counting the fuselage or whatever. You're counting all these pieces that are like flying off the rocket in different stages and stuff, or you're counting the stuff that's coming out of there. And the F thrust here okay. If it looks exactly like what I just wrote, yeah, it just about is. I just removed the vector stuff on there, and maybe it makes sense. Well, where the heck are they getting this from? I mean, yeah, that's great, whatever. I guess my gut feeling is the change in velocity, if it's a very, very fast exhaust, if I'm standing on that frictionless sleigh, and I pick up all these baseballs, and the faster I can fire them away from me, the more propulsion I'm going to give myself in the opposite direction. So if VE is very strong, it's going to go strong in the opposite direction. ln of this, if this ratio is somehow pretty drastic, like a very small fraction, which means its reciprocal will be very big, the absolute value of the ln, MRF, or MRI, let's get something straight, guys. All the logarithms have this tendency. The logarithm of any ratio is the opposite of the logarithm of the reciprocal of the initial ratio. This might be 5 for an answer, and this one right here might be -5 times a -1. In terms of absolute value, the absolute value of this is 5. The absolute value of that, before you throw the negative on there, the absolute value of -5 is also 5. So you're going to get a big, if the reciprocal is really small, if the ratio is really small, or if the ratio is really big, if they are reciprocals of one another, they have the same magnitude. The natural logarithm of 1 over a million is a pretty big number. Whatever a big number is, right? But the natural logarithm of 1 over a million is a pretty big number. The natural logarithm of a million over 1 is the same size big number in terms of magnitude, but it's positive. The logarithm, the natural logarithm of 1 over a million is a very negative number. The natural logarithm of the reciprocal of 1 over a million, in other words, the natural logarithm of 1 million, that's a number which is the same exact magnitude as the natural logarithm of 1 over a million. The magnitudes are the same. Saying all that, you guys, I don't think I'm saying anything too profound when I tell you if the natural logarithm of all this is a big number in terms of magnitude, and that's a big number in terms of magnitude, big times big is a lot of change in velocity. Yeah, if you lost a lot of mass in this expulsion process, and the velocity at which items are being expelled is very big, if this is very big and this is very big, of course there's going to be a big change in velocity. Put it another way, if the rate at which something is being expelled is very, very strong, if there's a lot of mass being expelled, the more baseballs I can throw in 10, if I can only throw one baseball every 10 seconds, yeah, I can propel that, let's say there's a hovercraft, it's frictionless. If I throw a baseball every 10 seconds, I can move myself. I can move the baseballs and I can move myself. Yeah, that's one baseball every 10 seconds. What do you say I throw 10 baseballs every 10 seconds? That's 10 times the propulsion. I'm pushing against 10 times more mass in that same period of time. I'm pushing away from me 10 times more mass. It's going to give me more propulsion. And that's where this is coming from. So the rate at which mass is being expelled and the speed, and if I can only throw that baseball at 5 meters per second, and then there's a major league pitcher that can throw it at 35 meters per second. If I can throw it only 5 meters per second and the Major League Baseball player can throw it at 35 meters per second, 7 times faster, it's going to be 7 times more thrust at that moment. So that's all they're saying. This is written, I'm just taking the vector notation out of there. Maybe it makes it easier to look at. Probably not a big difference. Probably not, but let's talk about it. So where are they getting this stuff? It's an important part. That's an important point, guys. It's an important point. Where is this stuff coming from? You remember this. We talked about this song and dance all over the place. How are we going to do something like this? How does this whole thing play out? You know, we are at the end of the day, you guys, we're saying this is going to be DMV DMV dt is dp dt. That's going to be equal to F, and that's this whole song and dance. So where are they getting this? Where are they getting this? Okay, we see this. It's in the book. This is strictly the best way to write it. Even when I bypass vectors, I mean, there's a good way for me to say something in English. If I don't say it formally in English, but I still communicate it to you without the best usage of the beautiful English language, without the best usage, I still communicate it to you. I got it communicated to you. But what's the best way to write it? Well, you know, there is a best way. There's the best grammar, and you can understand me if I don't use the right grammar. Well, this is the right grammar. It's a vector quantity. Be aware of that, okay? Push comes to shove. We're always, you know, it's kind of like that joke. You know, it's like the vector notation is telling us what's mine is yours and what's yours is mine. You know, what's mine is yours. Just don't forget that it's mine. Okay? We don't forget that we're still dealing with vectors, always. All right? So, looking good. So we got this. We're looking at it. How does this work out? What's this rocket doing? What are we doing? Let's make sense out of this thing. All right, you've seen what you've seen. Run out of room a little bit, guys. Sometimes I got to erase a little more than I want to erase, but where's this coming from? How's this working? Is it believable? Is it going to work? The rocket starts out at rest, you guys. It might be floating in outer space, and for our purposes, the momentum does not change for the entire system being considered when we're doing something like this. So we talk about a rocket. It's got no momentum. or it's momentum at a constant velocity. It might be going at a constant velocity. It's just floating there. We could, in our reference frame, in the reference frame of the rocket, there is no momentum if it's just floating there. If we haven't exploded the rocket engines to make the engines go, to make this thing start moving. So, there's a lot of ways to write this. I'm not always thrilled by all of them, to be honest with you, but let's see what we can do. Let me see what I can say. You're starting right here, and I'm saying initially it's a closed system. So dp vector dt is equal to, let me just see what you guys see this okay? I'm assuming everything's okay. Yeah, it looks all right. Looks all right. Just want to see how good the lighting is, guys. I want to make sure you guys can see me okay. Let me use some chalk that's a little bit stronger. And I'm saying it's this. It's actually the zero vector. Okay. The rocket's just floating in space. We're going to go dp dt. We're saying it's zero. Its momentum doesn't change. Why? Because it's a controlled explosion. The net force on the entire system is zero. That doesn't mean that each piece doesn't have a force. Sure there is. The kid pushed me. He had a force put on him. He put it on himself, actually. And he flew off me. He also put a force on me, and he put me in the other direction. You add the two forces together, they add up to zero for the system. But himself, by himself, has a force on him. He put it on himself. He also put a force on me. So let's see. I mean, there's a lot here. So dp dt is equal to the zero vector. dp dt is dmv dt is equal to, okay, now we've done this. This song and dance we've done, so we don't need to, we don't need to deliver all these speeches again here. We do have to be careful, though. We do have to be extremely careful. Yeah, correct. We said it was equal to zero. Why was it equal to zero? The initial momentum of the entire system was zero. The momentum after 100 seconds of the rocket firing, if I take all those mass particles that are flying out of the exhaust of the rocket, do a vector sum, and then add them to the vector sum of the rocket that's all together going in the exact opposite direction, all momenta add up to zero. This is true, but you better be careful. This is definitely true. At least for that rocket, this is definitely true, but you better watch what's going on here. And I dance with this thing a little bit, and whatever we're going to say about it. We've got to be really careful here with the notation, you guys, to actually get here. This is the change in the rocket mass. This is the velocity of the exhaust. Be careful, be careful. Be careful. At a particular instant, I want to know what is the rate that the baseballs are getting thrown out. What's the rate that I'm throwing the baseballs, pushing against the baseballs to be able to push myself that way. Myself, I'm the rocket. The baseballs are the fuel. At what rate are the baseballs being thrown? What rate are the baseballs being thrown? So, the rate at which the baseballs are being expelled, I don't know, 100 baseballs every second. Each baseball is a kilogram. It's 100 kilograms every second. Okay. How fast is each baseball going? Oh, I don't know. It's really going fast. It's not a major league pitcher throwing this. It's something else. Whatever. 50 meters per second, they're coming out. That's the velocity of the exhaust. This is the change in velocity of the rocket. It's not the change in velocity of the exhaust. The exhaust is a constant velocity for our purposes. How intricate could you make a problem like this, man? I guess you could make your head spin. We're not doing that right now. We are going to say, though, that the rocket taking off the positive direction, I want the rate of change of the rocket speed. This is the mass of the rocket that remains intact while this is going on. This is the mass of the rocket as it remains intact. Mass of the rocket that's intact. This is the change in velocity of the rocket per unit time. The rocket that is in, this is the rocket that is intact. Its change in velocity. This is the mass of the rocket that's intact. This is the rate at which the rocket is losing mass because of exhaust, and this is the speed of the exhaust. That's something you got to watch out for. Something you got to watch out for. Stay with that. Leave this here. Stay with this. Multiply by dt on each side. Multiply by dt on each side. Minus plus, the whole thing, we'll deal with it. Okay. And there's a lot that goes on here, guys. We're going to have to, let me carefully do what I got to do. It's almost putting the carriage in front of the horse on this one. Forgive me. Here's one, here's two. Leave what I said right there. I just multiplied by dt on each side and got to here. All right, time out. Leave this alone. Leave this alone for now. And let me come over here. Let me come over here and let me not multiply by dt on each side yet. I'm going to, and when I do multiply by dt on each side, I get this. I got it. But let me stay right here. Let me add a negative dm dt ve on each side, and then I solve for that. And what happens here is you get m dvr dt equals negative ve equals negative ve in relation to the rocket. Negative ve in relation to the rocket times dm dt. Dm dt. The dm is the change in mass of the rocket, the rate at which the rocket is changing mass. That's a fancy word for saying what is the rate at which exhaust is being expelled, and that's that. Guys, didn't Newton say mass times acceleration? Mass times acceleration is force. dv dt is acceleration. Mass times acceleration is the force. This is the thrust. Let me kind of go sort of backwards in this whole thing. That's the thrust. They threw a negative here. Is that a problem? No, as long as you know what you're talking about. They wrote it like this because they put a vector on here. The vector on here accounts for there being a negative. In terms of the actual magnitude, it's simply this. It's always confusing with these negative signs, you guys. This vector is whatever it is, and it happens to be oppositely directed. It's whatever it is. It's a negative compared to what the other one is. Well, negative times this means the thrust is going in the exact opposite direction. That's all they're trying to say, guys. So you can just as easily, if you're just talking about, as long as you, this sounds kind of almost ridiculous the way I'm saying it, as long as you know where the rocket's going in exactly the opposite direction. The rocket's going in exactly the opposite direction. Rocket's going in exactly the opposite direction is the other one. But this is the magnitude. The magnitude of the thrust that the rocket, the intact rocket, is experiencing is VE in relation to the rocket times dmr dt. And that's what I got there without using the vectors. You saw it with the vectors, so just be careful. I'm trying to make it easier. That may be backfiring on me. I don't know. You use your own judgment. That's why you're reading this, and make sure you have the practicality of the physics that's in mind, the practicality of the mathematics and the logical process. You got to determine that for yourself. Nobody can tell you how to think. I mean, you guys know that better than anybody. I mean, you know how you want. I don't like people telling me how to think either. I mean, that's my disposition, I guess. But I mean, we all have that some level, right? So make sure this is making sense to you. Okay? Make sure that's making sense to you. So that's it. So that's where this guy's coming from. That's where this guy's coming from. So we got that. We're able to derive that. Let's keep playing the game. How are we getting that? Again, the negatives are going to be a little wacky again. Remember the way I initially wrote it for you, as I just copied the book verbatim, it had a vector quantity associated with it, and that really accounted for negatives, positive, and everything else. You don't need to put the negative in there if you put vector notation. The vector notation contains the negative. The vector notation contains the negative. As we look at this, let's see what kind of sense we can make out of this thing, I guess you could say. Let's get this guy over to here, and then let's divide by m and figure out what's going on here. We got dVr. Let's add a negative dmVE on each side, and then divide by capital M. Negative VE in relation to the rocket, and we remember that one. That's just, you lose this and put a vector symbol, and that accounts for it, okay? So don't worry about that as much. As long as you know what, and I'm not trying to, obviously nobody takes this as an insult. We know what direction the rocket's going. Do we? Yeah. If the exhaust is going one way, the rocket's going the other way. Good enough for me. And from there, they're going to, you know, when they're asking you something like that. All right. dVr, get it over to one side, divide by m. So you got dm over m. Okay, that's a constant. This is variable. What do you say you integrate? What do you say you take this, and let's see what we can say here, guys. Who's the idiot writing so dark on these boards? Yeah, that would be me. Take a look. You know? So I got to work on that, but they're doing a great job cleaning up. So let's see what we got here, guys. The guys helping me clean this thing up, man, they do a great job. Otherwise, I'd be swimming in the chalk. They call me the chalk man for a reason, I guess. All right, let's do this. If you're going to actually do this, you are going to integrate from VI, let's see here, I have a lot of ways you could write it, from the velocity of the rocket initially to the rocket, to the velocity of the rocket initially to the rocket, the velocity of the rocket initially to the velocity of the rocket finally. Easy for me to say, I guess, right? So initial velocity of the rocket to final velocity of the rocket, dVr. You're integrating that. You're integrating both sides. We just said VE doesn't change. It's not a, you know, so VE, you got negative VE of the rocket. Okay, we're not going to worry. We're going to take that out of there. And we're going to go mass initial, mass of the rocket initial, mass of the rocket finally, dm over m. Well, dm over m, the integral of dm over m is the logarithmic function, the natural logarithmic function. Fascinating mathematics related to the natural logarithm and to the natural logarithmic function and the exponential function. E to the x and ln x are inverses of one another, and there's some just beautiful mathematics related to it. For our purposes, let's get the job done. What's going on here? If you integrate this, you got VR from VRI to VRF. You integrate this, well, that's nothing. You integrate this, you got ln ln m, you're going to go between MRF and MRI. Looks good. Well, I don't know how intelligent it was for me to put this one right in the middle of the board, but I think it is. We're actually deriving the stuff that's a part of it. So let's see what we can say here, guys. What's going on here? VR is this. That's the function, VRF minus VRI. That's just delta VR, you guys. What happened? I'll prove it to you. I mean, here's VRF, here's VRF, here's VRI. VRF minus VRI. The difference between the two is delta VR. This is negative VE in relation to R. Put this guy in here. That's ln MRF, and this is ln MRI. And I am going to run out of room. I don't want to. I want to do this in such a way that I'm not running out of room. So, all right. Just remember what I said here, guys. We're right here. We have all this. This is the VR evaluated between VRI and VRF. VRF, VRI. The VR function evaluated between the limits VRI and VRF is VRF minus VRI. Good enough for me. This is right here, negative VE R. ln M, the ln is being evaluated. The ln is being evaluated at MRF, MRI. Here goes. ln MRF minus ln MRI. You guys remember. The difference of two logarithms, again, some of the beautiful aspects of the exponential and logarithmic functions, some among the things that are very beautiful with it. The difference of two logarithms is the logarithm of the quotient. The difference of these two items, VRF minus VRI, is just delta VR, the difference between these two. This is negative VER. The difference of two logarithms is the logarithm of the quotient. Yeah, where's the negative coming from, Malus? You don't have it here. I'm not worried about that. As long as I know what direction the rocket's going, the size is going to be the size. If you want to say my rocket's going at 5,000 meters per second, I'll agree with you. What direction is it going? It's going toward Mars. No, it's going toward some other place. Doesn't matter as far as the speed's concerned. This is going to be a fraction less than 1. The natural logarithm of a fraction that's less than 1 is a negative number. Negative times negative is positive. It's going to be a positive increase in the direction in which it's going. Another way to look at it, however, is get rid of the, don't worry about the negative. If that's a vector, forgive me, if that's a vector quantity, multiply it by a negative, it'll direct it in the exact, yeah, the exhaust ain't going in the same speed, ain't going in the same direction as the rocket's going. There's no way. The exhaust is one direction, and the rocket that's intact is diametrically going in the opposite. That's where the negatives come in. That's not a big deal. I mean, the best way to do it, the very best way to do it is if you put the vector symbol here, and that'll account for it. If you don't put the vector symbol here, you've already kind of done it here, and it'll say that'll be a positive answer. The big thing is how this thing ends up. Okay? And that is a big thing. That is a big thing. So in terms of vectors, how they write it, that's the justification. That's the justification for a lot that's going on, you guys. This guy here will tell you the thrust force is going in an opposite direction. There's a lot of ways they write it. Let me see how they do write it. I don't know. They're a little. There's some kind of ambiguity here. They shouldn't be. I don't know. This is almost. I can almost argue it's not even as accurate as it should be. As far as where it's located, guys, I'm not gonna. Let's not nickel and dime the signs too much. Now, what does that mean? If I say to you the rocket, maybe there's like some rocket sled or something. The rocket sled is projecting the exhaust due east. Which way will the rocket go? Due west. You're not going to say due east. That does matter. If we're going to say due east is positive, what's due west going to be? It's negative. We can account for the signs. Get the magnitude of what's going on, you guys. I got to make it very clear, you guys. This is the way they got this. Let me just see how they got this. They say this. You can also write it like this. If you were to flip this upside down, if this is 1 over a million, if this is 1 over a million right here, 1 divided by a million, 1 millionth, 1 divided by a million. You flip it upside down, it's a million over 1. The magnitude of the logarithm, believe it or not, is exactly the same. One's a positive number, one's a negative number. So there's a lot of ways this can be done. There's a lot of ways you can get yourself out of the woods. There's also a lot of ways you can put yourself into the woods. So just be careful. Okay? Be very careful how you're doing this stuff. But that's a lot of what's happening here, you guys. Just trying to think what else. That's kind of the highlight I wanted to, of one of the chapters I wanted to bring up here, guys. How this stuff adds up. They go into it. There's a lot there. I got to use my professional judgment, you guys, to look at some of this stuff. There's a lot of these problems that I just can't talk about in person, but you got them on I was about to say D12. We used to have this stuff on D12. There's a lot of this stuff's going to be on Canvas. It's all a huge amounts on Canvas. You got to be looking at it. We got to be looking at it, and I know that you will be. You guys are going to do great. So that's some of what we're saying regarding this stuff, you guys. Let me see what I can say elsewise, guys. What else I can say in here? Some of these collisions. Let's talk about a few more things that can be occurring for us when we're doing this. So there's a lot here, some pretty neat stuff. It's a lot of fun. Watch what you're doing. If they give me the change in velocity of the rocket, and they give me these two items, can I find him? Yeah, it's algebra. What if they give me everything except for MRI? Yeah, I guess I'd have to find it, right? I guess I'd have to find MRI. And the way I'd have to do it is I'd have to divide by VER on each side. Then I'd have to exponentiate. Take each side to the E. For example, hey, I want you to find MRI. Well, at that point, if you're here and I want you to find MRI, why don't you do this? How about delta VR over VE in relation to the rocket? See how well that writes. Some chalk writes better than others, you guys. Let me just see here. Yeah, I'm not crazy about that. I like the other chalk better, but so I'm going to stay with the other chalk. I see it fine, but you're not right here in front of me either. So we got all this. Played all these games with this stuff, you guys. Okay, did a lot of math here on that, so okay, we're good. What if I wanted to find MRI? What do you say you take this guy, delta VR, I want to find MRI. It's not going to be the easiest thing in the world to do, but it won't be the hardest either. Oops. If I knew how to write, it would help too, but okay, here we go. There it is. Why don't you divide by VER on each side? I'm going to divide by VER on each side. I got ln MRF over MRI. Now, I just told you I want to find MRI. Why? Because they gave me everything else. They gave me what MRF was at a particular... This is a constantly changing process. There's going to be a time where there's no more fuel in this rocket, and they got to figure out a way to, whatever it is they're doing, I guess, if it came to that point, right? But if we got these two guys right here, if these two are equal, take a look at it, right? They're equal. If you exponentiate each side, delta VR over VER exponentiate each side, well, let's talk. I mean, we've got to be kind of careful here, but we need to be extremely careful, I guess. I mean, we got to really watch what's going on here, because I did something with the vectors, but the exponentiation of the exponentiation base e of the natural logarithm of a ratio is just the ratio. If these two things are equal, their reciprocals are equal. If I get the reciprocal of this guy, I get MRI. If I get the reciprocal of this guy, it's 1 over this, which is the same as e to the negative dVr, VER. Multiply by MRF on each side. I got MRF equals MRI. Those are positive for sure. I got E. Everybody's going to be positive. Well, it better be positive. I'm getting, this thing is, it's not a negative mass here. It's not a science fiction movie, right? So we got multiply by MRF on each side. We got, forgive me here, I just did something I shouldn't have done. Okay, yeah, right. So multiply by MRF on each side. So you got MRI equals MRF times E to the negative delta VR over VER. Okay, now here you got to be careful. This is a true story. It's definitely a true story, but you better interpret it correctly. Where is the mass the biggest? Where is the mass at the biggest? In this whole problem, the mass is at its largest amount at MRI. MRF, the initial mass of the rocket is very massive. The final mass of the rocket after 100 seconds of firing the rocket, is now MRF. If this is small and you want to get a big answer here, this e to the negative dVr VER has to be a number that is, and you got to be careful here. this quantity has to be a number bigger than 1. Has to be at least as big as 1 or bigger than 1. How can that thing be bigger than 1? You are guaranteed it being less than 1 if e to the negative dVr over VER is, if e to the negative VR, if e to the negative delta VR over VER, if that whole thing is a negative quantity, e to the negative number is 1 over e to a positive number. The exponential function, whenever it is, the exponential function of something having 0 or greater in its exponent, in its argument, e to the 0 is 1. E to the 1.1 is bigger than 1. E to the 1.2 is bigger than 1. E to the 2 is bigger than 1. But e to the negative 0.1 is less than 1. E to the negative 1 is less than 1, etc. This cannot be less than 1, guys. This has to be bigger than 1 because this guy is smaller. Because this guy is smaller than him. This has to be bigger than 1. Not a problem. Not a problem. dVr, delta VR, is smaller. The exhaust, the baseball that I throw, the baseball that I threw is going a lot faster than my sled's going to go after I throw the baseball. VER has a magnitude of velocity bigger than delta VR. This right here, delta VR over V, don't put the negative in there yet. It's there, but ignore it for a second. Delta VR divided by VER is a fraction less than 1. E to the negative small number is still a number bigger than 1. Bigger than 1 times a small number will give you a bigger answer, and it's got to work out that way. Once you start putting in numbers there, it should work out. If something haywire happens, we can maybe do, I'm not saying for sure, but you can sometimes do something with the signs and make it work out. Usually it's an issue of magnitude, it's an issue of interpretation. But the ln of x over y is equal to negative the ln of y over x, like I said earlier. So something can be done on that. All right. That's some of what's going on there, you guys. Let's continue to play some games with this stuff, and we'll figure it out. So let me just erase this and then get right back with you guys, okay? So we'll see what we can do. Let me think here. Actually, let me keep going, actually. No, actually, let me get back to you guys, actually. Let me get right back to you guys. Let me erase that, and I'm going to continue with this same video as we are. Okay, so let's just pause this. Okay, guys, thank you for waiting. I had to put it on pause a little bit and get back to this a little bit. All right, so here we go. So you saw what I've done so far with momentum, collisions, conservation of momentum, etc. What else can we say that's of interest? Well, there's a whole lot we can say, actually. We could talk about one-dimensional collisions, maybe make things a little bit easier. I think when we're doing these problems, as we need to be doing these problems, we're going to know a lot more. Now, let's try to make this relatively easy to look at. Forgive me here. I'm going to need some of the good chalk. Well, guys, we've said a lot. I mean, we've said this many times in one form or another. And earlier, we said that force, dp vector dt, True. There's a lot you can say here, a lot you can do. If you multiply by dt on each side, this can also be written as, roughly speaking, change in momentum is equal to force vector times dt. Further along the line, I mean, there's different ways they can say this, guys. Let's see how we want to say this. And then let me label it, I guess. First of all, let's just say this. We've already said this. We've already said this. It's more or less believable to us at this point. Having said this, if you multiply by the differential element dt on each side, so we've already said this, if you multiply by the differential element dt on each side, you get that. If you take this right here, you're basically, if you played the cards right and integrated here, you're essentially, from ti to tf, you get the change in momentum. You get there's an initial momentum and a final momentum, I guess you could say. Basically, at the end of the day, you'd get a change in momentum is equal to, starting from an initial time to a final time, that would be equal to an average force. Just see how they write average. I've seen average written in different ways, I guess you could say. They write it like this. Average force times delta T. Well, I've already kind of gone in this direction over there. This is the differential element that we could talk about. This would be written like this, which is the same as like this, where you would actually if somehow you could get an average here. That's where we're coming from here. It's really a more accurate way to write it. If you could somehow figure out what the average of the f vector function is. If you could find the average of the f vector function, then you could, from there, let me just see here, there's some, sorry once again, guys, there was something to which I was forced to attend. So this is this right here, and that's delta T. Well, anyway, force times time is called the impulse, and this is the change in momentum. Impulse equals change in momentum. If you exert a force over a period of time, there will be a change in momentum. So, a force exerted over a period of time will be a change in momentum. The larger the force for a given time duration, the bigger the change in momentum. Or, for a given time duration, the bigger the force means bigger change in momentum. Or the other way around, you could say if the force remained constant, but you did the force for a longer duration of time, also you'll get a bigger change in momentum. A big change in momentum will occur if the force is increased for the same time period, or if the time period is increased for the same force, or if both are increased or whatever. It's about the product of what happens. The more impulse means more change in momentum. It's as simple as that. So that's some of what's going on in that regard. So, and like I said, it gets written in a lot of ways. From the standpoint from the standpoint of calculus, you guys, it's coming right here. If you can take this thing right here, do an integral from Ti to Tf, and then divide that by the difference between the two, between Tf and Ti, by the difference, that'll give you, by the mean value theorem, the average force. Basically, I mean, if you just call delta T, if delta T was equal to Tf minus Ti, then if you took the integral from Ti to Tf of f vector, not dot, there's no dot here, there's only one vector here, that's the f vector. So integral from Ti, stuff's easier said than done sometimes easier done than said. The integral from Ti to Tf of f vector dt divided by delta t, where delta t is equal to this. Don't forget that. That right there, this right here, that integral divided by delta t by the mean value theorem is essentially the average force. The average force times delta t will give you the average force from the time period Ti to Tf. The average force from the time period Ti to Tf is delta t. That's the time period. The average force times delta t, will give you, the change in momentum. How do you find the average force? As we said, if you integrate from Ti to Tf, the function f vector dt, and then divide by the difference Tf minus Ti. So this integral divided by delta t is the average force. It's a weighted average in a sense. It's a way to find the average. The very important mean value theorem gives you that. And that's what I'm doing right here. If you integrate, then divide by the number of the amount of time. If you integrate over from Ti to Tf, do the integration, and then divide by the difference, Tf minus Ti, you'll find the average force. The average force times delta t will give you the amount of change in momentum. And that's what this was about, written in a little more generic sense. This is written in the differential sense. And all of it, guys, came from here. All of it came from here. So that's that. I mean, that's how we're looking at this thing, you guys. Very useful stuff. You'll see it. Again, this is one big reason why I'm such a fan of doing stuff, first of all, in person, which we can't do in person, which is kind of tough. And another reason, but one reason is just doing a lot of problems. The theory, all of this stuff, all the theory will come out in one way or another when you do enough problems. All right, so if that is the case, let's see what else we can say regarding this. Okay, guys, looking pretty good here on this stuff. Now let's see how things work vis-a-vis collisions. In regard to collisions, we know that certain things can happen, and what can happen in a collision? Well, a lot of things can happen in a collision. Things can fly off in different directions depending upon the elasticity of the collision. They call a collision where kinetic energy. They call a collision where kinetic energy is preserved. entirely preserved. The initial kinetic energy of the system equals the final kinetic energy of the system. That's called a perfectly elastic collision. A lot of times they just call it an elastic collision. If that's not guaranteed. I mean, I said earlier, here's what's guaranteed in a closed system. The initial total energy equals the final total energy. Yeah, that's true, but man, that can be manifested in a lot of ways. That can be manifested in potential energy, chemical energy, frictional forces which generate thermal energy. We can talk about magnetic energy, electrical energy. We can talk about kinetic energy. So kinetic and potential energy in various ways that potential energy can be manifested. It can be manifested with springs, with height. It can be manifested working with gravitational fields, with electric fields, with magnetic fields. There's potential energy, kinetic energy, as we said. Energy initially present. Energy that is initially associated with the system. E sub I equals energy that is finally associated with the system if it's a closed system. If it's a closed system, in regard to the universe, it's called the entire universe one big closed system. In regard to our universe, energy is conserved. In regard to a single room, where you're not going to let things like leave the room, so to speak, or whatever, energy is also conserved as well, depending on how things are set up. As a general rule in the universe, energy is conserved. As a general rule in the universe in general, energy is conserved. In a closed system, energy is conserved. E sub I equals E sub F. Energy initial equals energy final. Potential, all the energies together. Energy initial equals energy final. We've said that. Momentum initial equals momentum final. And angular momentum initial equals angular momentum final. We haven't gone here yet, but we will at some point. Yeah, these are all universally true. Whether you're talking about black holes moving throughout the universe, galaxies, entire galaxies moving throughout the universe, or you're talking about subatomic particles. Angular momentum is conserved. Linear momentum is conserved. Angular momentum is conserved, and we'll talk about it. Linear momentum is conserved, and energy is conserved. Kinetic energy is not necessarily conserved. It is conserved when kinetic energy is conserved when it's a perfectly elastic collision. Momentum is always going to be conserved. I don't care what you're talking about regarding the collision. This thing right here, I already said it over here. Okay, always conserved in the right system. So let me just leave it at that. This is conserved. It doesn't matter how they hit. Objects can explode or they can come together and collide. If they collide and they bounce off each other, but they don't bounce off in a perfectly elastic collision, momentum is still conserved. One way or another, momentum is still conserved. If they run into each other, they just stick together and then they all move off, momentum is still conserved. That's a perfectly inelastic collision when everybody collides and they all stick together. Or two items collide and they stick together. That's a perfectly inelastic collision. Certainly kinetic energy is not conserved in that case. Energy is conserved, momentum's conserved, angular momentum is conserved as well. In all instances, all collisions, all happenings vis-a-vis the universe and the entire universe or vis-a-vis a closed system, energy, momentum, and angular momentum. Energy, momentum, and angular momentum are always conserved. So when they collide and all of them stick together, or just two things collide and they stick together, momentum is conserved. Kinetic energy is not conserved, though. But energy in general is conserved, but not kinetic energy. The only time kinetic energy is going to be conserved is if two things collide in a perfectly elastic collision. So you're going to get this is only for this will occur only Only in a perfectly elastic collision are we talking about this. In all collisions, we're always talking about this. In all collisions. If they collide, bounce off, but it's not perfectly elastic. It's not like a perfect super ball. Perfect super ball is bouncing off and bam, going off. And something's dissipated. They lose kinetic energy. Sure, then that's not the case. These won't be equal. But this always will be equal. So will that, so will that. Always, for everybody. Whether it's a perfectly elastic collision or perfectly inelastic collision where they collide and they stick together. Still, all three of these will be preserved. And if it's anything in between, all three of these will be preserved. Always preserved. Universal law of nature. This is only for perfectly elastic collision. Well, let's talk about what happens in a perfectly elastic collision. Let's say, okay, this is the criteria. Is there something we can say about it and take it from there? Let's see what we got here. Well, let's say it is a perfectly elastic collision. Let's say it's two items colliding with one another, and they're like just super balls. Bam, they hit and they bounce off, and kinetic energy initial equals kinetic energy final. Can we see what's going on here? Well, if it's a perfectly then we got this. KEI equals KEF. Agreed. And we also have momentum is conserved. Yeah, we always got momentum is conserved regardless of what kind of collision it is. Period. Throughout the universe always. But you only get this. This is every collision, every single collision. This is the top criteria holds when it's a perfectly elastic collision. Well, let's see what kind of I don't know what kind of conclusions we can draw regarding this thing then, if that's the case. If you had, let's say, mass 1, M1, coming at mass 2. Now this guy's going V1I. Initially. The other guy, I don't know, smaller, bigger, it doesn't matter. Let's just make them look a little differently, if you don't mind. This guy's coming, the other guy, this is M2, he's coming at M2I. When they collide, they bounce off. This is not a good, any kind of good drawing here. This is M1, this is M2. This guy flies off at V2F. This guy flies off at V2I. And let's say it's just one-dimensional collision. They hit. They stay in one dimension. They stay in a straight line when they collide, and we figure out what's going on that way. Well, I don't know. I'm saying these criteria hold. If I say those criteria hold, why don't you hold me to it? KEI equals KEF and PI equals PF. 1/2 M1 V1I squared plus 1/2 M2 V2I squared equals 1/2 M1 V2, V1F squared plus 1/2 M2, 1/2 M2 V2F squared. This stuff's easy to do, but man, the alphabet soup of everything going on makes it a little confusing, so just watch out. What am I saying here, ladies and gentlemen? I am saying that if you add the initial kinetic energy, if you add all the kinetic energies initially present, they are going to equal the addition of the final kinetic energies. Period. If you add the initial kinetic energies, the result is the same as adding the final kinetic energies of the system, closed system. Okay? That is this is KEI equals KEF. KEI equals KEF. Sounds good to me. M1V1I plus M2 V2I equals M1 V1F plus M2 V2F. All right, so it's definitely a bona fide mess, but there it is. Well, is there a way to look at this to help it? This only works for perfectly elastic collisions because the first criteria is allowed only in perfectly elastic collisions. All right. Looking at this thing, let's see what we can do. I'll tell you what I'm going to do. Let's get the subscripts with 1. Let's get items that have the subscript 1 over to the left side. For the top here, let's get all the subscripts with 1. Let's get all items that have a subscript 1 present. Let's get them all over to the left side. All items with subscript 2, let's get them over to the right side. So subscript 1 over here to the left, subscript 2 over here to the right. Same thing here. Subscript 1 over here, subscript 2 over here. Let's see what we can. Let's see if we can make some sense out of this thing. Tell you what I'm going to do. Let me make it a little bit easier to do some of the math here, because I'm going to try to do a couple tricks here. Tell you what I'm going to do. What do you say I multiply by positive 2? I multiply the top equation by positive 2 all the way across, and then subtract m1 v1f squared. m1 v1f squared, I will subtract by m1 v1f squared on each side, and I'll subtract by m2 v2i squared on each side. Okay, let me say that again. I will subtract by, after I multiply by 2 on each side of the equation, I will subtract m1 v1f squared. I will subtract that on each side. And then I will also subtract on each side m2 v2i squared on each side. All right, what do we got here? What we end up getting is, we get m1 v1i squared minus m1 m1 v1f squared, and the other one is m2 v2f squared minus m2 v2i squared. Again, it's not really difficult, but just the alphabet soup that's going on, guys, is a little irritating, I guess you could say. Okay, where am I going with this? Well, I'll tell you where I'm going. I'm going to take an M1 and take it out of there. I'm going to take an M2 out of there. Okay. Yeah, it's true. It's true. It takes a little bit of time, not too much time, but we got it to there. We drew that conclusion. Let's go down here, maybe try to buy some time here. Let me take m1 v1f and subtract it on each side of the equation. And here, let me take m2 v2i and subtract it on each side of the equation. And we end up getting this. Right? Yeah, it's a little bit of a mess, but okay, yeah, looks okay. What's going on here? Well, okay, let's keep playing the game here a little bit. What do you say we take an M1 out of here? What do you say we take an M2 out of here? This is of interest, definitely. Definitely. We've got this, we've got this, and we've got that. Okay. Let's see if I could do some things here. This is a different, guys, you guys remember that a squared minus b squared is the quantity a minus b times the quantity a plus b. It's a difference of two squares. That's why something like this, v1i squared minus v1f squared, it's like a squared minus b squared, which is a minus b and a plus b. A squared minus b squared is the quantity a minus b times the quantity a plus b. V sub I squared minus V sub F squared is the quantity V1I minus V1F, the quantity V1I times the quantity V1I minus V1F times the quantity V1I plus V1F. Stuff's easier done than said. But that's what's going to happen here. Just interchange the subscripts. V2F, V2I. Okay, great. We may or may not, look, we're already seeing some, for lack of a better word, we're already seeing some commonalities here in some of what's going on. So, here I see an M1 and then something. I see an M2 here and something. Here I got an M1 and something, and here I got an M2 and something. So there's some stuff going on here. Let's talk. We're already kind of, I believe we're okay. I believe we're going okay with this. So you got it to here. Let's deal with it. This is M1. This song and dance right here, I just told you what it is. And in fact, I'm going to write it down again. It's V1I minus V1F times V1I plus V1F. The other one is M2 V2F minus V2I times V2F plus V2I. Sorry guys, I ran out of room there. That's that one. This one already kind of speaks for itself. V1I minus V1F. All right, that's really sticking out at my face, man. M1, V1I, V1F. M1, V1I, V1F. Does that look familiar? Yeah, they look exactly alike. These are exactly alike, except that this one's got that there. But this product, the first two items, the first two factors in the product are exactly the same as these two factors. These two factors and these two factors are the same, and you got this left over. These two factors are going to be the same as and the last one just stays. That one just stays. So, it's pretty significant, rather significant. This is only for a perfectly elastic collision, guys. I don't want to erase, I'd like not to erase any of this, but it's got to get erased at some point. Well, look, guys, it's not the prettiest way to look at it, I guess, but let's figure this out. If that equation and that equation are present, if all of this equals all of that, and all of this different thing equals all of that different thing, then all of this divided by all of this different thing is the same as all of that divided by all of that different thing. I'll make a long story short. If all this equals all that, if all this equals all that, and all this equals all that, then this divided by this is the same as that divided by that. If this equals this and that equals that, then this divided by that is the same as this divided by that. If you divide the two, M1 and M1 cancel. All that and all that cancel, and you're left just with this. Divide over here. This and this cancel. This and this cancel. And you're left with this. At the end of the whole day, you guys, you are looking at a situation where V1I plus V1F equals V2F plus V2I. That's neat. I have seen it written in different ways. The other ways in which it's written are certainly valid and they're certainly good. They certainly teach us something. Okay? They're certainly valid and they certainly teach us something. Personal preference here, I've always liked writing it like this because it's easier to remember. The sum of the initial and final velocities of the first object equals the sum of the initial and final velocities of the second object. And that makes the solution of problems that could be a little tricky, makes them a little easier, because this gives you one more piece of ammunition in your arsenal when you're attacking the problems. Okay? So, again, I always say this, the devil's in the detail. And you got to know how to do this stuff. You don't know this stuff until you can use it. I had a professor of a long time ago. He was a World War II veteran, actually. And he was a good guy, pretty decent person. And he taught me a lot. I mean, I didn't always get along with the person. I didn't always agree with what the person had to say, but knew a lot, knew a tremendous amount. And I would always say to him, hey, I know how to do this. And he would make it very clear to me, you don't know anything until you can use it, until you can actually use what it is you're claiming to know. Can't remember the exact words, but it's something like that. You really don't know something until you can actually apply it, until you can actually use it. My making the claim that I know something doesn't matter unless I can actually apply it, unless I can actually use it, unless I can actually make use of it and do something functional with it. What does that mean? Can you solve problems or not? It's kind of the theme of this whole class. Any sort of serious mathematics or physics or engineering that you're ever going to do, or anything else for that matter, is being able to solve problems. You got, especially in math, I mean, just from the academic standpoint and some other standpoints, you don't know anything until you can solve problems. I don't know the mathematics until I can use it and solve problems. I don't know the physics until I can use it and solve problems. Well, this is one more thing in our arsenal to solve a lot of stuff, you guys. Okay? And they go into this a bit. And they talk about it. They get into it in the book a little bit. Some of the stuff I said, I don't know to what level they take it. There's some neat stuff. I mean, there's more stuff here than is really feasible to talk about on film all the time. Even talking about it in person is not the easiest way to go sometimes. You've got to, this stuff, for it to be meaningful, guys, we've got to be looking at the book quite a bit, quite substantially. That's the only time effective way to do it, and then we try to look at everything that I've given you here. All right, I think I'm just trying to make sure that is it. I think that is it. They say different things here. At the back of the chapter 11, page 324 for the Katz book. Those of you who don't have the Katz book don't know what I'm talking about right now, but they say an inelastic collision. In an inelastic collision, the system of colliding objects loses kinetic energy. So there's perfectly inelastic collisions, which, I mean, they just stick together. I mean, that's about as inelastic as anything can become.
And in other collisions, they may not stick together, but they're still going to lose kinetic energy. If there's any loss of kinetic energy, whatsoever, it's an inelastic collision. To what degree, that's another matter in its own right. And that's an inelastic collision if it loses kinetic energy. It is a completely inelastic collision when the system of colliding objects loses kinetic energy, and after the collision, the objects are stuck together. That's completely inelastic collision. An elastic collision, sometimes called perfectly elastic collision, but I've seen it said, typically they just use the word elastic and they mean perfectly elastic. Elastic collision is a perfectly elastic collision. An elastic collision is an ideal case in which the system of colliding objects conserves its total kinetic energy. And we just solved for that scenario just now. All right, guys, I had to stop the video for this right here twice, but we could piece it together pretty good. There was just some stuff going on that I was not able to avoid. It's that simple. So I wasn't able to avoid it, guys. But it is here. You got it. The notes should be decent for you. I think they'll help you out a lot, you guys. That's the goal. Momentum, collisions, conservation of momentum. I said we'll piece it together for you. It'll look real nice for you. Okay? All right. That'll be it. We'll talk to you soon. Take care.